Okay, so last time we started talking about exponential functions. We showed that their general form, we didn't show, I said that their general form was this c a to the x minus h plus k, where all these c, a, h, and k are constants. They're just numbers. And so like a specific function of that could look like this 2 to the x plus 5 here. We described what each of those would do. C will vertically stretch or shrink the function. H will horizontally translate it. K will vertically stretch. Wait. That should not say that. Yeah, absolutely. So this should have said vertically translated. Also, there could be one up here. I didn't write it, but let's say bx minus h. That b will horizontally stretch or shrink. Now, and also, if there's a negative in either here on the C or on the B, that'll flip it. The negative on the C is vertical. It flips it vertically. And the negative on B flips it horizontally. Okay, that's technically called reflection, but whatever. Now, the only thing I didn't talk about was what A does. So let's look at that. Let's go to Desmos. Let's just type in y equals 2 to the x. Then let's see what y equals 10 to the x looks like. Oh, whoops. No, that's not right. To the x. So it's sharper, exactly, yeah. Or if we did y equals 1/2 to the x. No, that's not going to work. I got to put in a... Come on. Oh, yeah. Okay, well, we're not going to worry about that for now. But, so, yeah, the larger that number gets, the sharper the curve will be. Now, if we look here, recall that no matter what, even if we had y equals 10,000 to the x, it gets steeper still, but they are all going to cross this y-axis at 1. Do you remember why?
Because it has to start off 1, but like no, I don't know.
So think of what we're saying there. We're saying that we're plugging in 0 for x.
Yeah.
So what's 2 to the 0?
Well, 1.
1, right. Yeah. Anything to the 0 power is 1. Mm-hmm. So yeah, that's why it always crosses at 1. Now that does not account for if we did a translation. So like if we translated it up 1, well now it's going to cross at 2 here. We don't want that point. So yeah, let's see all these translations in action. So we shifted it up 1. That's what that does. But what if we added instead a shift up here? Let's do -2.
So it's just now.
Oh, dang it. No, that's not what I wanted to do. Well, yes, if we added -2 there, it would shift it down. But
2? Yeah.
there we go, like that. Okay. So now it crosses the 1 at this point right here at 2, 1. Because what we did is we shifted it to the right by 2. Whenever it's inside the argument, and the argument is what we call like the stuff that's inside the function.
Exponential.
Yeah, what's inside the exponential. Yeah, exactly. Whenever it's in there, it's things sort of behave the opposite of what you'd expect. So -2 shifts it right, whereas +2 would shift it left. So now it's over here at the -2. Okay. And then what if we did this? Let's say we did 2 on the outside there. Like that. So, well, how do we copy it? Let's do this. Okay, so this one, why is it too, give me a different color. Come on.
I think you just like the like line next to it, like the thing, and then you change the button there.
That thing? Or
No, that's what I'm talking about now. You click that, so I guess if you want to like point a line out, you can just like click that, and then I don't know what it is.
oh, if I do, oh, like that. I see what you're saying. Okay. So yes, thank you. So you can see that this, what happens whenever we multiply by the 2 is it kind of shrinks it. Yeah. And whereas if we multiplied by, say, 0.5, it widens it. Whereas instead, if we did this, if we go to the stretching on the outside, if we multiplied that by 2 instead. Wait, what?
Yeah, it's right there. So.
There we go. So that...
Wait, will that equation just be the same as 4 instead of the 2 outside of 2?
No, it won't. I'll show you why. So what that equation will be is if we have 2 times 2 to the x, whenever you have 2, and actually we'll be using this fairly shortly, whenever you have 2 exponential functions multiplying by each other, if they have the same base, which is what this thing is, this is a base, and this is the argument, like we said. Since they have the same base, the exponents add. So this is the same thing as saying 2, and the exponent on this one is is like 1, right? Because there's none there. If you don't see 1, then it's a 1. So it's 2 to the x plus 1. So if we went back in here and we did this, okay, see, I knew that was going to happen. Just being dumb. There we go. So yeah, now it's the same line. Okay. But yeah, so that's how some of these transformations will change these functions. So we could say that for example, if we had this function, let's say we had put the rule lines back on. So what are all the transformations on this function? We'll list them out up there.
Vertically translated up.
Good. Vertically translated up.
5. I don't remember the whole formula. I was like looking at that.
Okay. Here.
Split tab minus h. To the horizontally, so that would be translated to the right once.
Right.
It is stretched with that shrunk. Yeah, it's shrunk because is it shrunk because it's a negative?
The negative doesn't shrink it.
Oh, it flips it.
Flips it which way?
Horizontal.
So the B will flip it horizontally. The C vertically. Yeah. Actually, you know what? I'm going to get rid of this C, this vertical stretching, because all that does is add to the exponent, which is really a shift. So we don't need that. Okay, so yeah, so you said it horizontally translates.
2.
1.
Oh, 1 down and then the first variable.
Yeah, 1 to the right, and then the negative flips it, or a reflection. Vertically. So let's see if that's right. So let's just get rid of that. And then we have negative 2 to the x minus 1 plus 5. Here we go. So we got the vertical flip. And if we get rid of that, we can see the translation easier.
Oh, yeah.
So we had shifted it up
Mhm.
5 and to the right by 1. So it should be 1, 6 right here. Yeah, so good. Nope, that's not what I wanted. Okay. All right. So, so another thing that we'll want to know about this, about the graph here, is the range. So the range for the base graph,
Is all x?
yes, you're right. So for the base function, let's say f of x equals 2 to the x. Our a doesn't really matter because it's not going to change the domain or the range. So the domain is all x, like you said, which we would write as negative infinity to positive infinity. And the range would be, well, let's look at the graph. So as we said last time, as we get further and further into the negatives, this function gets closer and closer to 0. Remember, because we plotted out these points here, and we saw that as x gets more largely negative, the fraction gets smaller and smaller because of the way that the negative exponents behave. But it never actually touches 0. It's an asymptote. So, and then on the other side, on the positive side, it just keeps going up. So what would the range be?
2 to infinity? Or,
Well, that would indicate that it only goes from 2 to infinity, but we just saw on the graph that it goes all the way almost to 0. It doesn't actually touch 0.
oh, okay, so just like 0 and greater?
Yeah, 0 to infinity.
Yeah.
And do you remember what the circle brackets mean versus like a square bracket?
Like it stops here, like doesn't go past 0? Or it's not, it doesn't include,
Yes.
like 1?
You had it. You had it. You almost had it. Yeah. It doesn't include 0 in this case. It goes all the way up to it, but doesn't include it. Whereas with this one, this would mean it includes it. Actually, I'll write both of them. Ah. Son of a, dang it. Okay. Now, of course, though, the transformations will change the way the domain and the range work. So, like, for example, our problem here, well, we shifted it to the right and up, but the domain already included everything. So the domain's not going to change. So it's still going to be negative infinity to positive infinity. But what's going to happen here? So we flipped it and we moved it up. So if we go back to our Desmos graph, let's put the flip back on it. So you can see that it gets all the way almost to 5, but it never actually approaches 5. It'll get closer and closer and closer, but I mean, even if we go all the way out here, okay, Desmos says 5, but it's not actually. It's, let me add the, I don't know how to add more decimal points, but you're just going to have to trust me. It doesn't actually go to 5. So what would the range be for this modified function here?
-3 to +3.
Well, does it go all the way up to positive infinity, though?
Wait, which one?
This one right here, the darker red one.
Wait, so the main is...
The range. The range is the y values, remember. Domain is the x values.
Yeah, and it's just like 5 and under?
5 and under, right. So we would write that as...
Like the bracket, not the... they're like, not the bracket, but the box kind of looking thing?
Well, that would mean that it includes 5, but it never actually gets there.
So then it's not that.
But you had it, though. It's negative infinity up to 5, so negative infinity to 5, and then the circle bracket. Okay. So yeah, that's an example of how our domain can change with whenever we change the transformations of it. Okay. Okay, so what we can do is look at some of the properties of exponents. So like we already said, if we have a function which is just like 2 times 2 to the x, since they have the same base, then, or let's redo this as a times a to the x. They have the same base, so their exponents add. So it would be a to the x plus 1. So when multiplying, with the same base, the exponents add. Okay. There's another rule that says if you have something like this, so you have a to the x and then squared like that, what happens to the exponents?
Did they also just square? Or like, not square, but like multiply by itself? Or...
They do multiply, yeah. So...
Oh, multiply by the outside exponent.
Yes,
Yeah.
exactly, yeah. So it becomes a to the 2x. You could also think about it as like we're multiplying a to the x times a to the x, which is like this rule. And so they add, which is just a to the 2x. It works both ways. But yeah, it's much simpler to do it this way. Wait, I wrote that wrong. when raised to an outside exponent, exponents multiply. Okay. So we have those two properties, and we can begin. Let's talk about how to do this. So we're going to solve exponential equations. By the way, if I ever go too fast or if you're not understanding something, please let me know. You're not going to hurt my feelings if I taught something poorly or if I said something poorly. So first strategy here is to try to get both sides of the equation to have one base each. With both sides having the same base. Like right there, I could have written that way better. But basically, what I'm getting at is, look here. So on this equation, on the left, we have an exponent with base 6. And on the right, we have exponent with base 6. And when we have this, when this is done, we can just ignore bases, ignore the bases. So both of these bases are 6. We can just ignore them. It's not canceling. I'm not a math major, so I generally call it canceling, but that's technically not correct. And if you get like a math teacher that was a math major, they will jump down your back. Yeah. So, but anyways, so we just ignore them, and it is 2x equals 1 minus 3 to the x. And then we just solve for x. So just add 3x to both sides. So we have 5x equals 1, or 1, x equals 1/5. Make sense?
Yeah, no, it does. Like I'm working it out, it makes sense. But, yeah.
Okay. Well, let's do another one. Let's say we have this one here. So now this one, our first strategy is trying to get both the sides of the equation to have the same base, like we had here. Both sides had base 6. But now we have left side base 5, and then right side it's just 25. Is there something we could do to make that have the same base on the right side?
You could like multiply it or square of the on the right 5. And then you also square it on the left. So I guess we multiply it on the left.
So say that one more time.
So you either multiply the one on the left or get the square root of the one on the right.
Okay. So get the square root of the one on the right. So what would we have then on the right? just 5 by itself?
Yeah.
Okay, your head is in the right place. You got the right idea. The only thing is, if we do that alone, then now we've changed the right-hand side of the equation. Because once, yeah. So it has to be equal to what it was before. So if we leave the base as 5, then what could we do to it to make it equal 25?
Oh, 5, 5.
5 times 5, or another way of saying that is 5 squared. There you go. There you go. Good, good. Okay, so now, same base, both sides. So what do we get? What do we do next?
1 minus x equals 2.
Good.
So subtract that 2, right?
You can do
no,
that.
add the 1-ish, -3. Or, no.
It's all good, man.
So you subtract the 1 from the left.
Yeah.
And then you just get 1, and then -1. So -1.
Yep. Good job. Good job, man. Cool.
I understand.
All right. Let's do. Actually, let's move on from there. Or how do you feel? Do you want to do one more or
Maybe 1 more.
one more? Okay. Let's see. Try to do one with the rules and strategies that we have for now. Let's do this one. So it's 8 to the x squared. So it's a little odd, but both sides have the same base.
Yeah.
So what do we do?
You can just go x squared
Mm-hmm.
equals 3x plus 10.
Good.
And then take out 3x.
So we'd subtract it from both sides?
Yeah.
Yeah.
So 3x equals 10. And then, well, it's 5, but like, I don't know how I just kind of like worked that out mentally. I didn't like think about it, but yeah, it's 5.
So I'll give you a hint. There's actually 2 answers here.
Oh.
So what we have here is a quadratic. Do you remember how to solve quadratics?
No.
Trying to think if you did this in.
Okay, no, I have. But,
Okay. So the way we solve them is by getting everything over to one side. So.
Oh yeah, and so it's x squared minus 3x and then minus 10.
Right. So we have x squared minus 3x minus 10 equals 0. And now, do you remember what we do? Yeah, it's called factoring. But yeah. It's all good, man. Don't worry. I don't expect you to come in here knowing everything. That's why you're in class, so it's all good.
So it's just x squared, or x minus 3, or is it x minus 3 minus 10?
No, so what you have to do is the x, the left terms here, have to multiply to equal x squared. So x and x squared.
Yeah.
The second terms that go here have to multiply together to equal -10 and add together to equal -3. So we could do 1 and 10, 5 and 2, but
Or
negative 5 and 3 would be the one that works. You're right. Absolutely.
I thought it was 2.
And 2. Yeah. No, you're right. Yeah, you're right. -5 and +2. And the reason why this works, I don't know if they ever explain this to you, but the reason why now we'll say that x equals -2 and 5 is because, well, imagine if this one equals 0. If this thing equals 0, then it doesn't matter what this thing equals, because 0 times anything is 0, right? Conversely, if this one on the left equals 0, then it doesn't matter what the right side equals, because anything times 0, same thing. So that's why we can set them both equal to 0 separately, and that's why there's two different answers. So that'd be our answer there. Okay? And the last thing I want to end on is that the exponent is the inverse of the log function. And we briefly discussed this last time. But if we have, for example, y equals excuse me, let's just do a simple log equation, like a to the x equals b. The inverse of this is log, and we call this a the base. It's also the base in the exponent form, so it would be log base a to the b equals x. For the life of me, I do not remember what they call the b part here. But the base stays the same between each, and the exponent goes to the other side of the equation. That's how you can remember it. And oftentimes, this will be useful in solving these equations. So, for example, this one here. So if we think about our rule before, what we tried to do was we would try to get the right side 10 as a power of 2. And there might be a way to do that, but it would involve like decimal or fractional powers. And a much easier way to do it would be to convert it to a logarithm expression. So that logarithm expression would be, well, we have log. The base here is 2, so log base 2. The other side of the exponential equation goes here, 10, is equal to 3x. And now, now we divide this by 3 on both sides. And we'd get x equals 1/3 log 2 to the 10. And we have to do a slight more amount of manipulation to put this into the calculator, but now we would be able to do that. Whereas before, let's see what the solution here that they provide is. Oh, well, see, they actually did use logs. Yeah. So, okay. And that's what we'll be talking about more next time. Okay. We'll be getting more into the logs and how they relate to exponents. We do some examples of that. Right. But that is going to be it for today.